In 2023, something hit the Earth that shouldn't exist. A single particle, a neutrino, slammed into a detector at the bottom of the Mediterranean Sea, carrying 100,000 times more energy than anything the most powerful machine ever built by humans has ever produced. Not twice the energy, not 10 times, 100,000 times more, and no one can explain where it came from. Because here's the thing, there is nothing in the known universe powerful enough to create it. Nothing, until now. A team of physicists at the University of Massachusetts Amherst just published a paper in Physical Review Letters, one of the most prestigious journals in physics, and their explanation is as terrifying as it is thrilling. They believe we may have witnessed something Stephen Hawking predicted over 50 years ago, but that no one has ever observed: the explosive death of a primordial black hole, a tiny ancient object born not from a dying star, but from the raw chaos of the Big Bang itself. And if they're right, this single particle doesn't just rewrite one chapter of physics, it rewrites the entire book. Let's back up. You probably know how regular black holes work. A massive star burns through its fuel, collapses under its own gravity, and creates a region of space-time so warped that nothing, not even light, escapes. These stellar black holes are enormous, stable. They sit there for billions of years, quietly consuming whatever drifts too close. But in 1970, Stephen Hawking proposed something radical. In the first fraction of a second after the Big Bang, when the universe was unimaginably hot and dense, pockets of matter could have been crushed together so tightly that they collapsed into black holes right there and then. No dying star required. These primordial black holes could be incredibly small, some the size of an atomic nucleus, and they wouldn't last forever. Through a process now called Hawking radiation, they would slowly leak particles into space, getting lighter and hotter over time, radiating faster and faster in a runaway chain reaction until they explode. But here's where it gets really interesting. No one has ever seen Hawking radiation. It's one of the most famous predictions in all of theoretical physics, and after more than half a century, we have zero direct evidence that it actually happens. That neutrino at the bottom of the Mediterranean might have just changed that. The detector that caught it is called KM3-NET. It sits deep underwater, designed specifically to catch high-energy neutrinos from cosmic sources. Neutrinos are sometimes called ghost particles because roughly 100 trillion of them pass through your body every single second without touching a single atom. They're almost impossible to detect. But this one was different. It arrived with an energy of around 220 peta-electron volts. The Large Hadron Collider, the most powerful particle accelerator humanity has ever built, tops out at about 13 tera-electron volts. This neutrino carried energy 100,000 times beyond that ceiling. There is no supernova, no gamma-ray burst, no active galactic nucleus known to science that can accelerate a particle to that level. So where did it come from? Now here's what no one is talking about. There's a second detector. IceCube, buried deep in the Antarctic ice sheet, is the world's other major neutrino observatory, and IceCube saw nothing. Not this event, not anything remotely close to this energy level, ever. If exploding primordial black holes were common and blasting out particles in all directions, both detectors should be seeing these events regularly. But only one detector caught one event, one time. That contradiction is exactly what the UMass Amherst team set out to solve, and their answer involves something even stranger than primordial black holes alone. They propose that these ancient black holes carry what they call a dark charge. Think of it as a shadow version of the electrical charge we're all familiar with, except it operates in a hidden sector of physics that we can't directly see. Instead of interacting with regular electrons, this dark charge involves a hypothetical heavy particle the team calls a dark electron. A primordial black hole carrying this dark charge wouldn't behave like a standard one. It would evaporate differently, exploding less frequently but far more violently, and crucially, it would emit particles in a directional pattern rather than spraying them evenly across the sky. That explains why KM3-NET caught the neutrino while IceCube missed it entirely. The explosion wasn't aimed at Antarctica, it was aimed at the Mediterranean. And this is where it gets personal for every single one of us. If this dark charge model is correct, the implications cascade through nearly every major unsolved problem in physics. These dark-charged primordial black holes could account for all of the dark matter in the universe. Dark matter makes up roughly 85% of all matter that exists, and despite decades of searching, we have never directly detected it. We know it's there because galaxies rotate in ways that only make sense if enormous amounts of invisible mass are holding them together. But what that mass actually is has remained one of the deepest mysteries in science. The UMass team believes a population of these ancient charged black holes scattered throughout the cosmos could be the answer. The researchers have previously calculated that explosions like this should happen about once every decade somewhere in the observable universe. That's far more often than anyone expected, and it means our current telescopes and neutrino detectors could realistically catch the next one. If they do, and if the energy signature matches the dark charge model, we wouldn't just confirm Hawking radiation for the first time. We would simultaneously prove the existence of primordial black holes, discover new particles beyond the standard model, and potentially solve the dark matter mystery, all from watching a tiny ancient object finally die. Think about what that means. One particle, one impossible burst of energy at the bottom of the sea, and it might be the key that unlocks the fundamental nature of reality itself. The team at UMass Amherst says we could see definitive proof within the next 10 years. Our instruments are already sensitive enough, we just need to know where to look, and now, for the first time, we have a theory that tells us exactly what to look for. We are living through a moment that future textbooks might describe as the beginning of a revolution, not the loud, dramatic kind with a single headline, the quiet kind, where a ghost particle nobody was supposed to notice cracks open the door to everything we don't yet understand about the universe we live in. What do you think is really happening here? Are we truly on the edge of the biggest discovery in modern physics, or is there another explanation nobody has considered yet? Drop your theory in the comments. Some of the sharpest minds on this channel have a habit of connecting dots that even researchers miss. One impossible particle, 50 years of patient waiting, and the universe might finally be ready to give up its deepest secret. Stay close. This story is just beginning.